So now, before the break, we have just learned about the functional principal component analysis, and we have also learned how to control the roughness for the LPC. And so you want to make the LPC estimate to be smooth. Otherwise, it will be hard for you to interpret the results. So now let me explain how we do the LPC in R. So basically, we were using the R package called FDA. So you will load the, if you don't have FDA, you have to install the package. And I already installed in my computer. I will not install again. So we just load the FDA library. And so we will focus on the Canadian weather data is the 35 delay temperature. We just show you in the slides. So so here we have the temperature curve is a periodic function. So we were using the Fourier-based function to estimate the periodic functions. So we were using Fourier-based function to approximate the curve. So here, this is the function called create Fourier-based function. So we'll create a Fourier-based function between time from 0 to 365, and we will create 365 Fourier-based functions. So we just using one line here, and then we will define the roughness penalty for the FPCs and also for the delay temperature as well. So here we were using the harmonic acceleration differential operator. This is, as we explained, this is popular used for the when we estimate the periodic function. So we were using a function called vector 2f LFD. So basically, in this function, it will write down the differential operator L as a coefficient multiplied by f plus a coefficient multiplied by df plus a coefficient multiplied by second derivative of f plus 1 times the third derivative of f. So the last term is always 1. Coefficient always equal to 1. So then in this function, you can just tell it the value of the coefficient as a vector to this function. So the coefficient is 0, w squared, 0. So then you just put this vector, it will transform to this differential operator automatically. Okay, so we run this code. And then after we define this differential operator to define roughness penalty, we can define the roughness penalty and a basis function. So this is the 365 Fourier basis function, and we have this harmonic differential operator, and this is the smoothing parameter, the value of the smoothing parameter we use. If we do the smoothing, and then we can smooth all the temperature curve in one line of function called a smooth dot basis. Okay. So we do this. So it will smooth all 35 cities at the same time. And we can plot the data. So this is the 35 curves we get smooth out. Okay. So we have 35 cities. So this is the name of the 35 cities, if you are interested to see. Okay, so now we're doing the FPCA on the 35 temperature curve. So the function we use is called a PCA.FD. Okay, so what we do is we will put the smoothed FD, smooth curve is coming from the smooth dot basis. So temperature FD dot FD $FD, and we tell the number of LPCs we want to get. So the number of LPC equal to 4. So then we do the LPCA and we estimate the top 4 FPCs. Okay, so we can look at what is the return. So basically the return is harmonics. Harmonics is the old name for the FPC. Okay, so harmonic actually means FPC. Okay, and the values is the eigenvalues. Score is LPC scores. Variance proportion is the variance explained by each LPC. And mean FD is the mean function of the curve. So you can see here, when we do the LPCA, we will remove the mean curve first. So in this FD package, it will remove the mean function automatically. Okay. So this is the proportion of variance explained by each FPCs. So you can see the first one is 88%, next one is 8%, and next one is 2%, next one is 0.5%. So it's decay very quickly. Okay. So this is the LPC scores. If you look at the LPC scores, it should be 35 times 4. So each row will be the LPC score for one curve. Each column is for one LPC scores. So then we can plot the eigenvalues. So this is the eigenvalues for the current function. So you can see it decayed very quickly. Okay, so the top 3 dominate all the eigenvalues. And then we can explain the cumulative percentage, explain the total variations. And so we're just using the cumulative sum of the eigenvalues divided by the sum of all eigenvalues. So you can see here, so this is a horizontal line represented the 99%. So if you want to capture the 99% of information from the data, we will choosing the top 3 LPCs. So then we can plot the mean function. So using $mean FD. So this blue curve here is the mean function. And then we can plot the LPCs. As I said, harmonics means LPC here in the FD package. So we can just $harmonic. And so here, the FPC is estimated as a linear combination of the basic functions. So if you want to know the value of LPCs, you have to using evaluate.fd to evaluate this LPC at any time point. We evaluate from day 1 to 365. So we get the LPCs, and so you can see the dimension of this LPC matrix. So it's 365 rows and 4 columns. So each column will be the LPC evaluated at the 365 days. And then we plotted the first LPC. So this is the first LPC, okay? And you can also plot all 4 FPCs. So this is the all FPCs. This is, you can see the LPC is a little bit wiggly. So we didn't put any roughing penalty term yet. So we can plot the first LPC score versus the second LPC scores. So this is the graph I always recommend you to plot. This is kind of a nice way to look at the clusters for the curves. Okay. And so here I choose the 3 cities, Winnipeg, Calgary, and Resolute. Okay, just to show you how their weather looks like. Okay, so this is Winnipeg, this is Calgary, this is Resolute. Okay, so here I want to emphasize that when we do the LPCAs, when we calculate the LPC scores, it actually is calculated based on the centerized curve after removing the mean curve, right? So we have to look at how the curve looks like after removing the mean curve, okay? So this is how the curve looks like after we remove the mean curve, okay? Yeah. So after we remove the mean curve, you can see for the Resolute, it is strictly negative. So therefore, when it multiplied by the first LPC is positive over the whole domain. So the first LPC score will be negative, right? Yes. Okay. So so this is the second LPC, and so second LPC basically has the negative weight in the summer and positive weight in the winter. Okay, so therefore, when we plot the second LPCs, you see here like Winnipeg had a very negative second LPC scores. The reason is because for Winnipeg, it is a negative in the winter and positive in the summer. So then it multiply by positive values of second LPC, it will become negative, right? This part. And this part multiplied by negative LPCs, this part will also become negative. So that's why the Winnipeg become very negative, okay? And so for Resolute, on the other hand, it is negative in the whole range. After multiplying the second LPCs, actually the second LPC score for Resolute is very large because this is this part is negative. So when it multiplied by negative, it become very positive, right? Yes. Okay. So this is the how we look at the FPC scores. Okay. So now let's look at how we do the control the roughness penalty. So, so we were doing the same thing. We will first smooth out the data using the Fourier basis functions. So we have 355 Fourier basis functions. We define the harmonic acceleration differential operator, and we're using the smooth dot basis to smooth the curve. So this is the curve we got before. And also I tried to type a different value of the smoothing parameter. Now, before using 10 to 4, now I'm using 10 to minus 2. Let's see how it looks like. So you can see it now become a less smooth now, right? Yes. Okay. So, so if I tried the smoothing parameter to be 10 to 6, it will imagine it will be very light smoothing parameter. Will have very smooth functions. So you see the function is very smooth now. Okay, so we do the LPC, do the smooth LPC, and so I will do the LPCA on the rough curve. So the rough curve is when we're using the smoothing parameter equal to 10 to minus 2. So we will do the smoothing on this curve, okay? I want to show you that even when the curve is very rough, if we control the LP smoothness of LPC, we can still get a pretty smooth LPCs. Okay, so we will using, when we do the PCA, we're still using the function PCA.fd, but we will adding one extra parameter called it controls the smoothness for the LPCs. So we will define still using the harmonic differential operator to define the roughness penalty, and we define the smoothing parameter to be 10 to 6. Okay, so then we will do the smooth the LPCA. So after we get the LPCA, we can look at how the LPC looks like. So this is the LPC. So you can see here that although the original data is pretty rough, but when I have the smooth control on the LPCs, I can still get a very smooth LPCs. So this will help me the interpretation on the LPC dramatically, okay? So now let's do a bit of reconstruction for Montreal data. So basically, we will first drop the data for Montreal data. So so the Montreal data is the data is the 12th data. So we're just using minus 12. It will drop the data for Montreal data. So we only do the LPCA based on the 34 cities. And so we will do the LPCA on the 34 cities. And then we will look at, we get the FPC and the mean curve, right? And then we will look at the Montreal data. So for Montreal data, we have 365 days. And so we were only using the first 132 days. Okay, so we are only using so we will evaluate the FPC on the first 132 days. And also the mean curve for the first 132 days. And then we will remove the mean curve from the Montreal data. And then we do a linear regression of the observed 132 days Montreal data with the FPC, and we find the LPC scores will be the coefficient here. Okay, so so the prediction will be this coefficient multiplied by the LPC plus the mean curve, and then we can evaluate this predicted curve. So here, I think this red curve is the predicted curve. Okay, we plot again. So this is the predicted Montreal curve as a linear combination of LPCs, and so we can plot this is the data, and so we only using 132 days, and we are able to predict the rest of the data pretty well. So this is the mean curve. Okay, so this is the task to show you how we do the smooth control on the LPCs. So hopefully you will understand we were using the function FPCA, PCA.fd to do the FPCA, and hopefully you will know that now get ideas that if we need to put the smooth control on the LPCs, and we will get pretty smooth LPCs. It will help us for the interpretations. Okay. So one mistake for many beginners is that they forgot to control the roughness of the LPCs. They got very vigorous LPCs, and the interpretation will become very difficult. Okay, so this is the how I do the LPCA in R. So I will